Welcome to lesson 3. So this is our first machine learning model. So we're going to actually employ a machine learning model to give us some data here. This will just take us through this Melbourne data and how it would be done. This first section of code is doing the same thing we've done before. So we're importing pandas. That's that library that deals with data for us. There's a lot of data functions in there for us. We save the file path to a variable, and then we do a read CSV command here to convert the CSV file, that's our data stands in, into a data frame inside of our notebook. So, and the pandas library does that for us. It formats it so they can work well with everything coming next. And then there's this other nice column. There's a nice command here for columns, and it's dot columns here, and it's working on the thing in front of it, which is Melbourne data. So the dot notation is kind of like the equals, where it's like whatever's on the right is working on whatever's on the left. So here it's going to print the columns for everything when we do Melbourne data dot columns, and the output here shows us all the different columns we have in that data. So we could use all of these columns. Okay. Now this is a problem we don't have when we do our exercise later, but this is a dot drop in a axis equals 0. This little command here will find all of the rows of data that are missing and delete them from the data set so that we don't have missing data in our data set. This is just a quick way of getting rid of it. The problem with it is you're getting rid of data. So let's say, for example, we've got here that there is a council area. So maybe there's some house that didn't list which council area they lived in. If we use this drop in a bucket, we're going to actually eliminate that house from our data set. Not just that one cell, but the whole row, the whole house goes. So we have to be careful how we use this so we don't eliminate too much of our data as we go to get rid of it. All right. The other thing we'd do as a data scientist, you'd go back and you'd find the ones that are missing data, and you'd go back and do research and put that data in as well manually. So that's another option. So we're going to learn more about dot notation here. Dot notation is like we've been using before. It lets us operate on something. So in this case, this is a way to pull one of the columns out. So you can see one of the columns we had up here was price, right here, price column. So down here we can say, hey, we want to pull our price column out. And we're going to set this as our prediction target. So remember, it's good to remember what we're trying to do here. We're trying to take all of the house prices in Melbourne, put them into a model along with the data for the properties of the house, like bedrooms and all that stuff, put all that in the model as well, and teach our model how to predict, based on this information, what the value of the house is. So we'll have some houses that that are sold, that we have information on, and we can start making a model that builds that capacity, which is kind of fun. This is setting up the prediction target. And by definition, these models all use y as the prediction. So we're going to save as a variable called y. We're going to go to Melbourne data, and we're going to dot price, means get the price column out of this whole Melbourne data table and put it in a list called y. So now we've got all the prices in order in that variable called y. And now we need to choose what are called features. Features are the things that we're going to be making predictions on. So it's things, for this in case, it's things like number of garages, square footage of a house, the bathrooms, the bedrooms, the type of roof, all the things you can think about a house that might affect its value. These are the features that you're going to use. Now in this one, they're going to limit the number of features. They could go ahead and use all of these, but they want to try and find maybe the most powerful one to make predictions with. So they've reduced that number here by choosing features out. And what they do is they created a list called Melbourne features. And in that list, they've stored rooms, bathroom, land size, latitude, and longitude. And just be careful, these have to exactly match the names up here. So notice here that rooms is a capital R, so you need to make sure you have rooms there. If it was bedrooms, you want bedrooms here. So they're going to go find, this is going to go find all of these column names and do something with them. All right. Now, features are defined as X, capital X. So here our target was Y, this is an X. And this is just a feature of the model. The model's expecting a variable called X, so we're going to give it a variable called X when we do this. Now what this does is, this is a data frame here. So it's a big data table of all our data. And when we do this square bracket, and we put in a list of Melbourne features, which is all of these things, it knows to then go and get all of these columns and put them in a new table called X. So it takes all the features that we listed up here, and then it goes to the big data frame called Melbourne data. It grabs out all the columns with those names and then creates a new column or a new data frame called X and puts it in there. So far, so good. So basically, this step allows us to reduce the number of things we're considering and sitting into our model. That could save us time and money and energy. If we found that there are some things that aren't highly predictive, then we could leave those things off the list. Okay. All right. So now we're going to take a look at that data. So first we're going to do is use the describe feature. So we go X describe. Remember, X are all the features we put in. So you can see this is the X data frame has rooms, bathroom, land size, latitude, longitude, just the things we told it to have in there, not all the other stuff. And then all these other rows, this is the describe operator here doing that. So when we describe X, we get all of these for those. And that looks pretty good. And then the next thing we can do, the new command we learned is x.head. And what that's going to do is it's going to show you actually the first few rows of your data. So you can kind of get a feel for what numbers are in there. There's any major problems that are popping up. So here, x.head showed that these are the first, I'm not sure why it's 1, 2, 4, 6, 7, but these are the first several rows of the data table. Oh, maybe that's showing us that some were deleted in the drop NA thing when we dropped out missing information ones. But these are the top seven, or the top five in the data table. All right, that's what X head shows you. It shows you just the head of the table, the very top of it. All right, next thing we do is start building our model. So in this section, there's a 4-step process. We define the model first and some of the parameters of the model. What type of model we're using. These models have all been built for us, and we're going to use someone else's model, and we're going to train that model using our data. So the nice thing about machine learning is you don't have to create a model from scratch. You can use previous existing models and just have your data train those models to work. Fit. This is the heart of, as it says here, the heart of machine learning. This is where you're taking your features and you're running them through your model and testing to get whether they're actually predicting correctly for the price that you know the house went for. So for fitting, you have to know the features and the predicted value for each feature. So you have to know the price of each house basically that's going into this model. That way, as you run it through the model and the model tweaks itself, it can see whether it's doing a good job at actually predicting the actual value of the house or doing a bad job. So that's what fitting is. Prediction is then, what you do in prediction is you would then predict some house prices based on some features and see if it's actually predicting things that are reasonable and close. And then you're going to evaluate by determining how accurate it is. So these are like the 4 steps in using machine learning models. All right, so we need to get our model. So in this case, there's a scikit-learn is a popular library from which a lot of models exist. We're going to, from sklearn.tree, we're going to import decision tree regressor. So sklearn is huge. We don't want to import the whole thing. So we're just going to import one thing from the sklearn.tree, and that's the decision tree regressor. That's the type of model we're going to use, our base model. So now we need to actually create the model. So we create a name for the model. In this case, we're going to call it Melbourne model. And then we go over here, decision tree regressor, and we give it a random state of 1. The only reason to define the starting state, so there's, the model starts out with kind of a random starting state and then moves and tries to improve itself from there. We'll see that happen in the future. If we give it a random starting string, we tell it to start at a certain particular place, that means every time you run the model, we'll get the same outcome every time. If we don't put that random state 1 in there, it's going to choose a random state every time, and it's going to have a slightly different process every time, and our outputs will be different every time by a little bit. So by having this 1 here, it means that we can easily compare one run to the next because they started in the same place. Okay, and the value of this doesn't really matter. It just makes it slightly different overall. Now, the fit.model, this is where we can actually fit the model. So here we're just populating, we're putting a blank decision tree regressor model into this thing called Melbourne model. So now we've got our tree in there that's unfit yet. It's just like regular, normal state. No data's flown through yet. And now this is where we're gonna actually fit it. So this is where we do Melbourne model. So that's that blank decision tree model, decision tree regressor model is in. And we do dot fit, and we tell it what it's going to fit. So X is that data frame that contains all the data on the features, the number of bedrooms, the longitude, latitude, and a few other data things I forgot now, or bathrooms, I think. And then Y are the prices for all the homes listed in X, and they're in the same order, so it can compare and say, hey, when I tried to predict it, I should have gotten X, or I should have gotten Y as the prediction, but I got something else, so I need to adjust my model and make it better. Okay? I hope hopefully that's kind of clear. And now we're going to come down here, and this is where after we run this code, we're going to have our model that's fit. So it's going to go through, starting with a random state, and do a bunch of trial and error trying to make it work the best for the data we gave it. So it's going to run the data through in a certain way, going through all the tree and going out. And this is going to say, okay, how did I do? I thought the prices should be about yay, and the real prices are over here. So, oh, that didn't work well. Let me try again. And it'll keep working itself until it gets it into a good place, hopefully. And now this is going to be just us checking what's going on. So this first command here, print, is literally going to print the words in the quotation marks, the string, right here on the screen. You can see here's the output for it. And then x.head is going to print those same 5 rows of data from above. And then print Melbourne predict x head. So what this does is, this is the Melbourne data. This is our model, and it's already been fit above. So this is our model now that's been like tweaked and twisted to make it work really well, hopefully. And then you're going to do a dot predict to predict data. The data that we're going to predict is we're going to predict these first 5 here and see how they do. So when we do this predict, it doesn't know anymore that what the price of the house is. All we're giving it is just those variables of bathrooms and bedrooms and lot size and latitude and longitude. That's going to make a prediction of those houses. We can use that hopefully to tell whether we're close or not. So here the predictions are, and that's just this line of code right here calls that. And then here's the output of those. So what this is telling us is this first house here in the row, it's recommending a price of $1,035,000. And for this one, it would predict a price of $1.465 million, $1.6 million for this 4-bedroom house, $1.876 for this 3-bedroom house, and $1.636. So we can kind of look through and see if that makes sense. I would expect it actually the 4-bedroom house to be the most expensive, and that's this third one on the list. So I'm surprised this 3-bedroom house here is $1.8 million. But when I look at it, I'm like, okay, 3-bedroom, 2 baths, all right. A 4-bedroom with 1 bath, that's problematic. Like, that'd be rough. But 3-bedroom, 2 bath, okay, that makes sense. But then here, land size. Now I'm starting to see it. This is double the lot size of that one. So that makes sense that it's more expensive. In fact, you can see this 2-bedroom, 1 bath, which should be way less than this 4-bedroom, is actually a little bit more than that 4-bedroom prediction. And I look over here, oh, it has an even bigger lot size. So it's got a really large piece of land with it. So maybe that explains it. So you can start looking for interesting, weird patterns like that pop up in your data. All right, next video will show us how to do the actual modeling of this and do it with our Iowa data. Hang in there.